So now I'll be presenting on my FYP topic titled Self-Supervised and Supervised Contrastive Learning. I will focus on the second part of my FYP, which is Supervised Contrastive Learning. So for the Supervised Contrastive Learning, I worked on a topic which is titled Transferability of Representations Learned Using Supervised Contrastive Learning from a Multi-Domain Dataset. So in SimClear, which is a self-supervised contrastive learning framework, labels are not available. The positive set consists of an augmentation of the anchor images, anchor image, whereas the negative set are images in the mini batch. So this leads to a less than ideal problem, which is the issue of false negatives, where negatives contain images from the same class as the positive. So as a result, Khosla et al. Introduced a new framework known as that make use of these supervised contrastive laws, in short, SUPCON laws, which leverages on label information. So in this case, positives are images from the same class, and they are contrasted with the negative set, which is of an entirely different class. So contrastive learning has shown to provide higher quality representations than cross-entropy laws. And there are many studies that shows that representations are transferable to a different downstream dataset. However, representations were often learned using a single source domain. So for example, the most widely used dataset ImageNet. And little work has been done to explore the transferability of representations learned from a multi-domain dataset using contrastive learning. As such, the objective of my study is to apply SUPCON and train a SUPCON model on a multi-domain dataset. And the multi-domain dataset that I'll be using is called DomainNet. And then I will evaluate the transfer performance of the SUPCON model. I'll compare the transfer performance of SUPCON versus a cross-entropy loss model. And I'll be using the fixed feature linear evaluation protocol. I'll evaluate the transfer performance on 7 downstream datasets across different domains. So more specifically, my study will aim to answer this research question. Does supervised contrastive learning give better transfer performance than the commonly used cross-entropy loss when trained on a multi-domain dataset? So to give some brief background on what is the domain rail, quick draw, painting, infograph, and clip art. Each domain contains 345 classes. So for the purpose of my research, I combine all of these domains into one huge dataset for pre-training. So here are the 7 downstream datasets that I've used, which is CIFA 10, CIFA 100, aircraft, flowers 102, SVHN, which stands for Street View House Numbers, and Kalkura, and DTG, which is describable texture images. So all of these are pretty commonly used dataset in the computer vision research community, except for maybe Kalkura, which consists of Japanese illustrations of paintings of facial Japanese illustrations. So here is a high-level overview of the supervised contrastive learning architecture. So as you can see, we start off with 2 images, X1 and X2. They are from the same class of dog. So each images undergoes augmentation to obtain 2 differently augmented images of itself. So over here we have 4 images. They are forward propagated through a base encoder, and then we obtain the vector representations of the 4 images, and then they are further forward propagated through a multi-layer perceptron projection head to obtain the projected vector representations. And then we apply the supervised contrastive laws to maximize the similarity between all 4 of them because they are from the same class. Whereas at the same time, we maximize the dissimilarity between these 4 and all the other images in the mini batch. So here's the experimental setup for the SUPCON model. On the top of this slide, you can see that that's the supervised contrastive learning pre-training stage. So we start off with the combined domain net images, and then they undergo augmentation, and they are forward propagated through a base encoder, which I used a ResNet50 base encoder, and then they are further propagated through a multi-layer projection head, which is just consists of a linear layer, a value activation, and then another linear layer. Then we obtain a 128 dimensional vector. So the subcon loss is computed, and then we compute the gradients and backpropagate them through the base encoder and the MLP projection head. So during the linear evaluation stage, we take the base encoder and freeze the weights of the base encoder. And we train it as usual using the cross entropy loss. And we only backpropagate to the linear layer, and the base encoder is frozen. So I just wanted to highlight that the augmentation that I used was called SimAugment, which consists of a random resize crop, random horizontal flip, random color jitters, random grayscale, and random Gaussian blur. I also did a hyperparameter search for linear evaluation, and the table over here shows the search base that I've used. So here's the experimental setup for the cross entropy model. It's similar to the one to the subcon model, except that there is no MLP projection head, and that the loss used in during the pre-training stage is the widely used cross entropy loss. Similarly, for the linear evaluation stage, the base encoder weights are frozen, and we use the cross entropy loss to backpropagate only to this linear layer over here. So similarly, we also do the hyperparameter search in the linear evaluation stage for the cross entropy model. So here's the results that I obtained for the supervised contrastive learning model. So on the left of this slide, we shows the subcon loss against epoch, and I used the stepwise linear learning rate decay scheduler. So the learning rate decays at epoch 250 and 350, and we can see that this actually corresponds to a sharp drop in the subcon loss at epoch 250 and 350. So this shows that the stepwise learning rate actually helps the model converge towards a lower loss value. So here's the results obtained for cross entropy model. So on the left again, we see the cross entropy loss against epoch, and on the right is the learning rate schedule against epoch. So here are the results that I have obtained, and to summarize this table over here, subcon actually outperforms cross entropy loss in all the downstream data sets that we tested, and subcon performs 6.05% better than cross entropy on average when trained on a multi-domain DomainNet dataset. So I also performed some ablation studies to study the effect of temperature. So over here at this with this graph over here in this slide, you can see lower temperature values of 0.04 and 0.07. The mean accuracy was lower than that of the higher temperature values of 0.1 and 0.13. And when temperature further increases to 0.17, the mean accuracy drops. So what this implies is that it's important for us to select an optimal temperature value in order to obtain the best transferable model that we can obtain. Next, I also studied the effect of augmentations. SimAugment and StackRandAugment are stronger augmentations, and they perform better than AutoAugment and RandAugment in terms of mean accuracy, except for the Street View house number dataset. I conjecture that this could be due to the fact that AutoAugment and RandAugment include sharing, translation, and rotation, which could potentially boost the transfer performance for Street View house numbers. Next, I also did some relation studies on the effect of base encoder. So I tried varying the base encoder to a deeper model, which is a ResNet 101. However, I noticed that there's no noticeable improvement with ResNet 101. And I cross-referenced to a study done by Kolosnivko on the effect of model and dataset size on transfer performance, which states that the benefits from larger model diminishes given constant number of pre-training images, and slowly increasing model capacity may degrade performance. I note that further studies on the effect of base encoder may be required. So for future work, I note that we could experiment on more downstream datasets from different domains, and the 7 downstream datasets that I've used in my study is definitely not representative of all the datasets that could appear in the real world. So it'd be interesting to see how the subcon model could perform on other domains such as satellite and medical images. Next, we could pre-train on higher resolution images. And because the training images were resized to 32 by 32, which is a rather small resolution, future experiments could increase the resolution to more higher values that are more widely used as 24 by 224. Next, we could also combine subcon and self-supervised contrastive loss, and as done in this Islam et al. In his paper. So in conclusion, in my FYP project, I did in the first part I did self-supervised contrastive learning with SimClear, and the next part I applied supervised contrastive learning for multi-domain dataset. So some concluding remarks that I have is that data distribution shift is a common problem in real world, and if you have a self-driving car that's trained on images of the roads of the icy roads in Norway, it will definitely not perform well in on the roads of Singapore. So on safety critical systems such as self-driving, it's important that we build more robust systems that's perform well in more many different situations. And that's the end of my presentation. Thanks for listening.